Okay, so welcome back from the break, even though I'm sure you wish it was longer. And we're about a little over halfway through the course. You had demonstration two over the spring break, and we'll have another version of that at some point. And we're starting a new topic, probability, which is based on counting and to a certain extent maps, mainly sets and counting. Um, and then not this weekend, but at the end of next week, we'll have concept check 3. And we'll be then heading into the last fourth of the course. Okay, so there's that. And there are two probability packets. There's probability exercises and a zip file with some Python probability programs that we'll go over during this week. So that's just be aware of those new things. They're on the resources section on Piazza. And I guess I should ask, are there any questions about anything? Of course, feel free to jump in later or now, but if you don't, then we'll continue and you can jump in later if you have a question. Okay, so let's start with probability. Some of you may be familiar with this if you've taken a statistics course, although probability is different than statistics. You do something that has some uncertainty in it, and you can predict what's going to happen with the probability, and then afterwards you can look at what happened and see if that matches your expectation. So if there's some event that you want to consider, probability is what happens before that event, and statistics is what happens after the event. So we're just dealing with probability, and we're only dealing with finite probability, a special case. We're not dealing with probability in general that you might see in applying to science or to sociology or some other subjects. Okay. So probability, what does probability deal with? It deals with patterns of uncertainty. There's uncertainty, for example, if I toss a coin, we don't know whether it's, and let it land on the table, say we don't know if it's going to land heads up or tails up, and the same with the dice and many other events. We can't predict exactly what's going to happen, but there are patterns. For example, if you toss a coin and the coin is a fair coin, it isn't weighted to land more one way than the other, then you expect that it's going to, half the time it will be heads up and half the time it will be tails up. So there's this pattern. And if you have a weighted coin, it might be a different pattern than you expect, but still there's likely to be a pattern. And so probability is about those patterns and how to extract some certainty out of uncertainty, and what you can do with that. Okay, so the first idea that you have is that you have so you have a set of ideas. So there's sort of some technical terms or ideas. The one thing you have is you have a probability experiment, and that's just you're just going to consider some event or action to be your probability experiment. So the simplest one, for example, would be toss a coin, roll a couple or one couple of dice, things like that. And there's more complicated ones. For example, if we wanted to know, well, like everyone's born on a different day of the year, but there's sometimes patterns to that, and you might want to know say how likely it is. And that's sort of the kind of question you ask, and probably how likely something is. If you have, like in our class, what's the likelihood that of the people in our class that two people have the same day of the year as their birthday? And obviously there's because I mean, if we wrote down everyone's birthdays, there'd be no uncertainty, but you could sort of ask about in general, you sort of select some group of 30 people and ask, what's the likelihood that two of them are born on the same birthday? Or if you choose 50 people. So that's one project that we have at the end of the chapter, is how to figure out the probability that two people in a group of 50, 30, 60, 100 people have a birthday on the same day of the year. Okay, so those are probability experiments. I spelled probability wrong. Okay. There's probability experiment. Now, what you have in a probability experiment, it's a probability experiment if you have fixed outcomes. The outcomes are like, for example, for a coin, you say the fixed outcomes are heads and tails. And we could label those by H and T. Now, when I say fixed, what I mean is this: if you actually toss a coin, there's onto a table or something, there's always the possibility that it could sort of like roll around and end up in a crevasse, or a crack in the, not a crevasse, but a crack in the floor, or lean against a wall and end up neither heads nor tails. So the idea of a probability experiment is that you neglect that and you say, okay, we're going to only take coin tosses that have heads or tails. And if one of those other events occurred, we're just to ignore that and say that didn't happen, or just ignore it. So there's sort of a definition of what you mean by a probability experiment is you have a fixed set of outcomes. Say for a coin, you have heads or tails. You could label that as T or H. For a dice, for a six-sided dice, it could land with one of these numerals, 1 through 6, face up, right? So the outcomes here would be either heads or tails, H or T, and for the dice, it would be 1 through 6. For a more complicated experiment, we always have a fixed set of outcomes. Okay, now, so that gives you this sort of technical term as outcomes and probability experiment. And the way we're going to model this is a sort of about the world, so to speak, is we're going to make a set S, set, which is called the sample space. And S is the set of all outcomes. So, for example, for the coin, we could give it just by the names of the outcomes, could be heads and tails. The S for a six-sided dice could be might be the numbers 1, 2, 3, 4, 5, and 6. If we had a four-sided dice, it'd be 1 through 4. Jillian, you have a question?
No, sorry.
Oh, okay. So there we have. So these are the sample spaces, and one of the important things is going to be the number of items in the sample space. So here S, the number of items in the sample space is 2. The number of outcomes in the sample space of dice is 6. Okay, so this idea of sample space, which is the set of all outcomes. Now, so nothing. This is just sort of how we're approaching things. So it's like the probability experiment or outcomes is sort of the physical thing that happens in the real world, and we're making a model of it by this set of all the outcomes. And the third thing, which is, so that's sort of not too bad, but the third thing is this idea of events. Now, an event is the idea of an event. So the idea of an event is a subset of sample space. That sounds weird, right? Because an event is something that happens. Well, since the sample space is a set of outcomes, an event could be something happening, right? Because it's a subspace, it's the outcomes that actually occurred. Now, usually you think of the event as if you roll a dice, it's going to be heads or tails, and that's true. But that those are outcomes and those are events, because so but then I'm thinking of them not as outcomes but as subsets, and we'll sort of see that distinction a little bit. For here, you might say, okay, well, you have the event that it's a 1, a 2, a 3, a 4, a 5, or a 6, and that, but then you could have another event that the outcome was even, which would include several outcomes like 2, 4, and 6, or that it was odd, so that would include the outcomes 1, 3, or 5. So the most obvious event, say for the coin, would be the subset where you just had an H, it was just heads up. And this would be the event that tails occurred. So we're thinking of them as, we're identifying them as subsets, okay? Then because now there's actually for the coins, there's two other events. There's two other subsets. So it's going to turn out that it's not just that an event is a subset. Any subset is an event. So here, there's two other subsets of this sample space here. One is the empty set, which is the set with no outcomes in it. And then there's the subset S, because S is a subset of itself. So we have, for the coin, we have 4 subsets: the empty set, the whole set, the whole sample space itself, and the individual ones. Now, for a roll of a dice, we of course have the individual ones, like this, up through 6. But we also have other, we're going to say this would sort of be the event H, and this, we could have not S, I want E for event. I want E even to equal the subset 2, 4, 6, and the event odd would equal the event 1, 3, 5. Or I could have the event that would be 1, 2, and 3, and the other event would be 2, 4, 6. So any subset. So there's going to be lots of subsets of the dice one. You know, there's only 4 for this one, but there's actually going to be a lot for the dice. In fact, we can actually count. We can actually count how many subsets there are for the dice. So if we want to know, like, how many like for the dice, which is the sample space is 1, 2, 3, 4, 5, 6, we can ask how many. You could ask how many events are there here. Well, that's asking how many subsets. Well, the way to count it is this: any subset can either have a 1 in it or not. That's 2 possibilities. But then, no matter what you do here, the next one, the 2, could either be in the subset or not in the subset. There's 2 possibilities there. Then there's 2 for the 3, 2 for the 4, 2 for the 5, and 2 for the 6. Now those are independent events, independent choices. Do I include the 1 or not include the 1? Well, I have 2, there's 2 choices there. So these are all independent. So the number of subsets of this out with 6 dice is going to be 2 to the 6th. Just 2 times 2 is 4, 2 fours is 8, 2 eights is 16, 2 thirds. So it's going, which is going to be 64 events. And this is true for any sample space. If you have a set that has a size, if it has n elements, then the number of subsets is going to be 2 to the n, because I could either include or not include in the subset any element. So if I don't include any, I get the empty set. If I include them all, I get the sample space itself. And if I include some and not others, I get other subsets. But anyway, so there's the whole picture for events. Now, that's just a structure to sort of upon which we're going to build what's called a probability model. So this was our first thing, was the probability experiment with outcomes. The second one was a sample space with events. And the fourth thing we want to do is going to be a probability model, given a sample space and this set of events. Okay, so let me